Yeah, I'm going to talk today about how to do massively parallel processing with something that's called procedural Python. And we'll get on to why that is, why it's called procedural Python later on. But the idea is that I'm going to just show you a few little things, a little demo with an IPython notebook, and hopefully it'll run because it's actually live talking to a database somewhere in America. So, as was said, I'm a data scientist at Pivotal. And Pivotal is a relatively new company. It was formed last year out of parts of EMC and VMware. Just quickly, if you haven't got these links, there's the IPython notebooks in that GitHub repository, and then there's a rendered version down there. I'll put these slides up on the web later on. So what is Pivotal? Well, Pivotal was formed out of lots of different parts of two companies, as I said, EMC and VMware. And the idea is to try and bring together some of the sort of big data components of those two companies. So there might be a lot of things you've actually heard of before, but never really connected with Pivotal. So things like Pivotal Labs, our agile software development team. Things like Cloud Foundry, our platform for cloud-independent apps. And if you're a Java programmer, you've hopefully heard of the Spring framework. Millions of Java programmers use it every day. And then we've got things like our data layer, or a data fabric, as we call it, which includes the Greenplum Analytics database, a Hadoop distribution like everyone else, and also things like our in-memory database system called Gemfire and SQLfire. So just briefly to tell you where I'm coming from with what I'm talking about later on, the customers that we have are normally large enterprises with lots of data, but maybe aren't using it to the best of their abilities. So they have terabytes to petabytes of data, structured and unstructured, and they want to do something more with it. Maybe they want to reduce the fraud that they're seeing in their banking transactions. Maybe they want to understand their customer better. Maybe they want to sell more clothes or understand how fashion is changing week to week and month to month. What they're not able to do at the moment is get what they want out of the data because they're unlike maybe, say, a smaller, more agile company, they're lumbered with large and relatively old legacy technologies that have high cost and pretty limited flexibility. One of the main things we see when we go into a company is that the response times for doing some data science or interactive data analysis, the response times are really low, so are really long, I suppose. So you send out a query and it comes back, in 6 hours or the next day or something like that. Whereas really what we want to help enable our customers do is to get down to interactive data science. So I'm putting in a query and I'm getting something out so that I can try the next query. So I can fail quickly and get on to the next query fast. Just quickly, a few other things you might have heard of that Pivotal is part of, or contributes to, or provides support to, are things like Redis, RabbitMQ, Grails, and Groovy. And in fact, we now have one of the main Hadoop committers as part of our team. There in the middle, we have this MADlib library that I'm going to talk a little bit more about. And if you want to know how to interface with MADlib through Python, there's this wrapper called PyMADlib that one of my colleagues wrote. That enables you to do that. MADlib is an open source machine learning library for use on large-scale, massively parallel databases. In fact, it works with Postgres, it works with Greenplum, and now also works on some Hadoop frameworks like Impala and HAWQ as well. So when we go into a customer engagement, what sort of technology do we have on our side? Well, normally, because I work for Pivotal, we have something like the Greenplum Database or our Hadoop distribution with HAWQ, which is a SQL on Hadoop solution. There are open source options for all of these things. So there's a Greenplum Community Edition and a Pivotal HD Community Edition. As I said, MADlib is completely open source. But where does Python fit into all of this? Well, we use Python in the same way that a lot of you do maybe for exploratory analysis in IPython using NumPy and SciPy and pandas and matplotlib. But we also use this other thing, which is PL Python. So this is a way of leveraging Python inside a database. So you already have your massively parallel database, large, it costs a lot of money, it's very large, it does lots of computation very fast. We want to be able to enable you to use Python, not just some SQL or SQL-like language in there. And the benefit of using PL Python is that we get to use all the great packages like nltk or scikit-learn and all those things inside the database. We don't have to bring the data back locally to our laptop to enable those analyses. And that's one of the big themes for us is bringing code to the data, not bringing the data to the code. Obviously that gets more important the larger the data sets you're looking at. Okay, let's switch then to the IPython notebook and see if that works. Okay, so we've probably skipped a little bit of the intro, but basically the idea is that you have a Postgres database, and now you think about how can I make this work better with larger amounts of data? Well, if I had 20 machines or 100 machines, I could put Postgres databases on all of them and then have a master node that actually connects to all of those and tells each of those what to do. So when you submit a query, you submit it to the master node. That parses the query, figures out where the data lives on that distributed computing system, and then sends the queries down to those distributed systems, gathers it up together, and gives you the answer. So, the simple way to think about something like the Greenplum database is to think of Postgres living on a cluster and being controlled by some master node, okay? And where PL Python comes in is that PL Python is basically allows you to write functions for your database that aren't in SQL. So in SQL databases, you normally have things called user-defined functions, UDFs. It's a way of writing some query in SQL that you then wrap in a function and can call repeatedly. PL Python is a way of writing a Python function inside that SQL wrapper. Okay? In fact, you can do this with other languages as well. There's PLR, I think there's even PL Java, and there's another thing called PLPG SQL, which is Postgres's iterative programming language that looks like SQL but not quite. You can assign variables and those sort of things. So obviously we won't get the interactive bit here, but you can see what's going to happen. So first of all, this whole thing is a bit confusing, because what I'm going to be doing now is I'm going to be using an IPython notebook to call some SQL database using SQL, pure SQL. And that pure SQL, in the middle of it somewhere, will have a little bit of Python. So there's actually layers of Python SQL to Python again. And the way we're able to do this is with this really handy little magic command called IPython SQL by Catherine Devlin, and it's on GitHub, so you can go get it. But what you need to do, first of all, is just load the magic command. And then I'm just going to connect to my database. And if you work in large databases, you normally create a schema. It's just like a sandbox to keep all your, it's like a namespace, really, to keep all your namespace together. OK, so first of all, let's look at what, put this a bit bigger, what a normal user-defined function looks like, OK? So obviously the syntax highlighting doesn't quite work here, but the idea is that you have some simple SQL commands, create function, you give it the name, and you give it the type of argument to put in, here an integer, an int. Tell it what it's going to return, again an int. And then in between these dollar signs, these two dollar signs, this is the actual body of the function. So here it's super simple. It's select 2 times my first argument. Okay? So as you might imagine, when you run that, you just do, because we're in SQL, you have to use a select. You get select the function and some argument, and the answer you get out is 20. So it works. To go on to PL Python is really simple. Basically, in between the dollar signs now, instead of writing SQL, you want to write actual Python. So here we have just a really simple, if A greater than B, return A, otherwise return B. The outside looks quite similar. You've got create function. You have to give it types. You have to tell it it's going to return an integer. And then at the bottom here, you specify which language you're doing this in. And this is called, the language is called PL Python U. The U stands for untrusted. So In fact, to install this on your database, you have to have admin privileges. But that's because with Python you can do anything. You can in fact access the base file system of the computer that your database is sitting on and running that query on. So if you're an administrator, that probably sounds a few alarm bells, but that's just the way it is, unfortunately. I think there are efforts to try and make a trusted version, but that would obviously limit the capabilities of the Python interpreter inside it. So we've created this function PyMax. Give it 2 integers, and it returns the larger one. And here we're going to test it. And again, it's just simple select from this function. Give it 2 integers, and then you get the result out. And if you've ever worked with SQL-style databases before, maybe you can start thinking about how you can make this more complex. This the function can live in a select statement, so you can start doing things like select function and then a column name, and you get whatever is coming into that column from your table. You can add it in, and you can put this inside another function, like a UDF. And you can also do things like returning composite types that your database will understand as rows. So here we want to return, I suppose in some way, a tuple of a name and a value. Again, you have to type them, so you give them a text type and an integer type here. But that means now that when we go and look at our creating a function down here, we can actually return. Here I've returned a list with the name and value. Inside Python, the types don't matter. So I can return just a list with name and value. And then when I do that, down here, let's just go down and look. When I do that, say make pair with a name, here's Zosimus, and a value, say 1, the output that I get is that pair coming back to me. Inside the Python parts, you don't need to worry too much about what sort of container it's in. So it can be a tuple, it can be a list, it can also be a dictionary with the names of the return values as the names here, name and value, in the dictionary. It can in fact be an object that has attributes .name and .value as well. So you can imagine doing something in scikit-learn and getting some object back or getting some result set back, and yes, you have to do some extra legwork to create this type up here. But once you've done that, your database actually understands the parts of that Python object that you're returning and is able to put them in the right place and knows the right types for them. Okay, so we tried out this function, and we got this pair back, which, in the database looks like you're getting a result set, I suppose. The next thing I want to talk about is how you can actually, first of all, you can note that UDFs and PL/Python functions are allowed to have multiple function signatures. So previously, my function had a name and a value. And down here now, we're just using a name. So sometimes people use this sort of maybe, I don't know. They use it to overload the function to do things like provide help. SQL isn't a nice programming language like Python where you can just introspect things, or you can, find comments inside the function or doc comments or whatever. So people do interesting things like having a function with no arguments gives you back the help, or a function with the word help in it gives you back the help documentation. Okay, but apart from that, we can also, as I said, leverage the power of Python packages inside these PL/Python calls. Now, to do this, you have to have installed the package and all its dependencies on each of the nodes of your database. So, I'd recommend doing that with some kind of package maintainer, maybe Conda, something like that. And the way we do it in Greenplum is that we have this parallel SSH kind of system where I log in, one login, and I'm actually logged into the 10, 20, 30 computers all at the same time. So that lets you install these things quite quickly. Once I've done that, once I have NumPy say, on my database, on all the nodes and all the segments of the database, I can use it inside these PL Python functions. So again, this is really simple, but say just, inside here, NumPy, just make this array, and then just return the name that we were given and some value from that array. And here again, I'm returning this named value type up here. Okay, so when we do that, now we get back the name and one of those elements of that array. So one thing to note about SQL database is the calling semantics for these functions, whether they're where they are in the select statement. Are they part of the from clause, or are they at the beginning? Actually affects how the results come back to you. So before we had select, make, pair, Horatio, or whatever, and we got back the results as I suppose as a tuple in some ways. If we in fact do select star now, we will actually get back the columns, and you can reference those then in a further outside query, or you can put them straight into a table, or you could do all those sort of things. So the database has now understood that there's two values, name and value here, and we can do whatever we want with them after that. So I've only so far returned one result. So one line of, I've sent a query out, I've got one line back of a result. Can I get more than that? If I do a complicated query, complicated numerical calculation, I'll probably get a lot of results that I want to get back and store in my database. How do I do that? Well, the easiest way to do that is return a set of something. So that just tells the database that, in fact, there's going to be more than one query. So be ready to get however many rows are going to come out of this query by the end. So here again, if I import NumPy, I can return here three different results, and the way they come back is just at, if I do again select star, the way they come back is at three different rows of the result set for my query. Okay, so we're actually playing within the rules of the database semantics. This allows you, as I said, to put these things together, put it in a subquery, save the results into a table, all those things that you would do with standard SQL results anyway, you can do with these Python functions. Okay, but that's great and all. We can use it to run some Python. But why do we want to do this? Well, really the reason we want to do this is to leverage the parallelization possible when you have this large distributed system. So, Pivotal, we have this data computing appliance where we have, 16 blades, each with 4 cores. So once you start leveraging that, you can actually get quite large speed-ups in how you do queries. One of the main things you need to think about, though, is that your data is going to live on this database, but in different places. How you distribute that data is actually very important. So whether you distribute it by one column or another can make a large difference, because if you end up doing a query which, for example, joins, say we have say we have customers, orders, and customer information. We have customer information in one table, we have order information in another table, and we want to join those two tables together. If we keep all the customers alphabetized across my system, but in fact the orders are done by order number, then each time I want to join those two tables together, we're going to have to go find which order refers to which customer, maybe go to a different machine with all the network traffic that entails to find the customer name and then get their information. Whereas if I distribute my data across the system based on, for example, a customer ID value. So all the customers with ID values 1 to 10 are on node 1, 10 to 20 are on node 2, like that. If I then distribute the orders in the same way, so an order that went to customer ID 1 lives on the first box, then doing those joins becomes much quicker, the data lives in the same place, there's no network traffic, and everything is good. So one of the main things when we go to customers and we talk about their data is how have they distributed it? Do we need to change that? do we understand the kind of queries we're going to be making so that we can make an informed decision about where the data should live in order to enable this sort of speed up with the parallelization as quickly as possible. Obviously, there's still some speed up if the data has to move, but you have multiple processing units. But in order to keep the data in the same place, it makes sense to, in order to speed up the calculation as much as possible, it makes sense to keep the data in the same place. And when you're talking about petabytes and joining 2 petabyte-sized tables, that makes a big difference. So let's see what this looks like in terms of the PL Python. So this is just generating some data. Basically, I have 3 series here, one A, B, and C. The first one is just floating point values from 0 to, I suppose, like 10,000. The next one is taking the sign of that. And then C is just the sign except boosted by 100, okay? And in fact, you can see here what I've done is I've said I want to distribute this data by the column called name. So up here, A is the column name. And when I tell the database to distribute it by name, what I'm saying is that look in the column name, see all the values that are there, do something, probably a hash of those values, and then put that data in the right place so that the hashes that are the same live on the same box. So, you have to be very careful the way you do this. You don't want to, you've got a petabyte-sized database, 60 different nodes you can store it on. If the column you distribute by is a gender, male-female column, then in fact you only have 2 places that you want to store it. So you've put all your 2 petabytes onto 2 of the boxes and left the other 58, or whatever it was, 62 empty. So you have to be careful that the cardinality of the set that you're using to do the distribution is large enough that it makes full use of the number of nodes that are available to you. So here in this case, maybe we've only got 3, so it's not quite true, but in a bigger example, you'd have to do that. Okay, so I've lots of data now, 3 million lines of something. If I just go and naively create a function, say I want to just find the mean of all those numbers. I know I could do that in SQL, but let's do it in NumPy for fun. What I have to do is give that PL Python function, the argument has to be an array of all the numbers that I want to use. So here what I've said is there's some array, value array, and it's a double precision array. Okay, so an array of floating point numbers. It only returns 1 float, but you give it an array of lots of floats. Inside, this is straightforward. We just return the mean of the array. But how I call this now, I slightly have to change my semantics. So if the column y is the number we're trying to get the mean of, I want to take it out of this test data table. But I don't want to give it to the function. If I called it, as we were before, say np mean brackets y, then what I'd get is the mean of one number. I'd give the function one number, I get the mean of that number back, and then do that for every single number in that table. Instead, what we want to do is give it all the data at once. So you use this function in Postgres called arrayag, which basically takes a column of column of results, puts them into an array, and uses that as one object and hands that to the function. Okay? So I've got a mean here. I've got this function. I'm going to give it an array of all the values in the y column for my data. And then we're going to see what we get back. And in fact, we get back the mean of all those numbers together. But really what we want to do is we want to do separate models for each of those types of data we have. Here it's obviously a contrived example, but maybe you want to do, maybe we have customers in lots of different European countries or lots of different states in the US, and we want to do a customer clustering model for each of those countries. We don't want to do an overall model. Or I think Jürgen was talking earlier in the hierarchical classification about doing a model for each product category. To do that now, we just use the SQL semantics of group by, which means we just put the name out the front of the statement here. And then down here we say we want to group by the name. So for each value in name, pull all those results together. The order by just means we'll get the results in sort of alphabetical order here. And then we do the function. And here y now isn't the results for the whole table. It's the y values for each group labeled by name. So we had A, B, and C. So now what we're going to do is we're going to give all the y values that correspond to name A, give that to the function, get something back, then do it for B, then do it for C. And in this way, you've naively parallelized your problem very quickly, because all the data, as I said before, we distributed it, lives on different boxes. Those boxes can go ahead and do the calculation and give us back the results. And what you get back is something like this. And in fact, this shows us what we were, our contrived example earlier. One of them has mean 5,000. That's the one that just goes up in step. This is the sign at around 0. Again, so the mean should be around 0. Yeah, that's OK. And this one is the one that is boosted by 100. So again, the result's OK. So you can imagine how to do this for more complex examples. And maybe we want to do machine learning models, or we want to use scikit-learn, or we want to do something like that. And we want to do it in all these different categories all at the same time. So let's do something more complicated. Here I'm just going to do a linear regression. OK, not very much more complicated. I'm going to do a linear regression on those arrays of numbers. So we're now giving it 2 arguments, the x and the y array. We're going to return a float of arrays, an array of floats. And we're just going to use SciPy, stats module, and simple lin regress, and see what happens. So again, if I do it for all the data, I get back a linear regression model that worked across all the data and gave me back, here we have the slope and the intercept, and some of the errors. But I know that I want to do this model not, as I said, not for all my customers across Europe, but I want to have an individual model for each country, or I want to have an individual model for each product line, or I want to have an individual model for each type of bank transaction, something like that. Can I leverage the power of the parallelization to do all those models in parallel? And yes, I can. So as we had before, simply use the group by semantics. So you have name, the function, and then group by down here. And I will go off, run your Python SciPy linear regression on each of those arrays. And what you get back as the results are the 3 results for the linear regression. In the first case, it is pretty much a straight line with this slope going up. In the second case, it's picked out the horizontal line that goes through the mean of all the sine functions. And here we can see that it's actually picked out, for the third case, the y-intercept is 100, as we had put in our data. OK, so that was really the end of my little demo. Hopefully we've used up enough time that I don't need to try and get my slides working for the rest. If you want to see what I was supposed to talk about from my PowerPoint, come up and talk to me afterwards, or connect with me on Twitter. It's just at Ian Huston, Huston. And I'm going to take a few questions now then. So thank you. Yeah. So the question is, how does this affect the execution plan that the query analyzer in the database comes up with?
Yeah, because it can become really suboptimal, right?
Yeah.
Yeah,
exactly. So if you have a large database, you have an execution or a query planner that looks at the query you're trying to do and tries to figure out the best way to do it. It does not know about Python. It knows that there's some function it has to call. It doesn't know how long it's going to take, and if you think about it, it can't really unless it understood all the insides and outs of Python and all the packages and NumPy, etc. So no, the query plan doesn't understand. The query analyzer doesn't understand the cost associated with doing these things. I think basically you're given the power. You've got a full Python interpreter inside each node of your database now. You could do anything. You could start writing files to disk. You could do all that sort of stuff. It's given you a lot of power, and with that comes a lot of responsibility.
But would it collect statistics and try to estimate
So would it, like, once you've done it once or twice, would it try and collect? I'm not sure. I can check. I don't think so. I think it kind of thinks of it as a black box. You know, you can imagine there being difficulties because it's not concrete what the runtime is going to be each time you call this function. Like, sometimes it might be very quick, sometimes it might be very slow, depending on the inputs, depending on what's actually happening inside. So I have a feeling it just kind of takes a step back and says, you know, you're responsible for running this query and knowing how long it's going to take. Yeah. It was a good question. Any other? Yeah.
You talked about moving the execution to the data rather than moving the data to the execution. I'm wondering what sort of throughput and scalability do you get doing that? Are you not restricted with number of clients that can throw queries at the system?
So I suppose, yes, you are. You're going to have some way of handling those. And you know, there is a queuing system for clients connecting to the database. Basically, everything's handled by the master node. The master node, you know, dictates to everyone who's trying to connect what's going to run. And you can have a proper scheduling system with higher priority queries versus lower priority queries. So obviously, you know, you want some queries to be run immediately. Some queries are maybe you want to slow down. The way, you know, maybe taking a broader view, the way we think about doing analytics is that you should try and have an analytics environment that enables you to do interactive queries. And it probably shouldn't be your production batch environment that is doing, you know, the payroll at the end of the week or whatever it is. You don't want your data scientist to think he can't run a query because he's worried that he's going to stop, you know, the pay slips being delivered the next day. So yeah, it's an important thing to figure out. I think sort of cost benefits you get from being able to bring the code to data mean that, you know, speed up just the process for data analysis and data science so much that actually, you know, instead of trying to bring all the things to your laptop, which obviously will crash at some point, I think the speed up we get is worth the sometimes, you know, sometimes there's a bit of chat on the email list about, you know, who's running that query, why did you let it keep going, please can you cancel it, like, you know, it's run amok, can you shut it down, that sort of thing. Yeah?
Yeah, just startup costs. So depending on your machine, you know, if you're setting your laptop and you type Python and PyLab, you might be counting to, I don't know, 3, 4, 5 before it starts up.
Yeah.
Now, obviously, the goal of your, you know, analytic platform, as you say, for sort of sandboxing is true interactivity, and you type a query and it comes straight back. Is there a way to sort of get a Python interpreter to be sitting there with all that stuff already loaded, and then when it gets the code, it just goes, I already know NumPy, I already know, you know, scikit-learn, whatever the libraries are? Because that seems like that should be possible, right? It should be possible to have it sitting there and ready to go with the stuff loaded if you tell it ahead of time. But I don't know how you would do that.
Yeah, so the question was, can I have a Python environment that's ready to go and loaded up with all the libraries, whatever, and I suppose inside the database on each of the segments. Yeah. And yes, that brings up a good point. Each time you run this function, you're actually creating an interpreter that has to load everything, and you know, if there are loading costs associated, then they factor in.
The interpreter itself is not small.
Yeah, yeah, exactly. So I think, you know, this way of doing it, that's not the way it's set up. You know, each time it runs one of these procedural functions, whether it's Python or R or Java or whatever, it spins out a process to run the associated interpreter. It doesn't have a long-running interpreter in the back end. You know, obviously, you know, there's a different paradigm way of thinking about it. You could just have a compute cluster, you know, using something like IPython cluster, where you have all the IPython kernels sitting out on your cluster, waiting for you to send it. But then again, you're sending data to it, unless you've, you know, managed to make the data live in the right place.
Or your queries,
yeah. Ian.
So one of the problems with running distributed systems is debugging them remotely. What is the debug support like for retrieving tracebacks or interacting, if possible, with a broken query?
This is a very good question. It's probably not as good as you'd have, you know, just running something locally. I think you do get stack trace.
Multi-processing is a pain.
Yeah, exactly. So if something goes wrong, I think you do get a stack trace back. Now, if something goes wrong on all the nodes, you'll get 64 stack traces back. So being able to work through that. SQL is not known for its, what's the word I'm looking for? Informative error logs. So, sometimes you might just get back something is wrong here somewhere. And it takes, really it's wrong at the first place that it actually, caught the syntax error or whatever. Yeah, I don't think we have a great way of doing it yet. It's something we kind of need to work on. Yeah?
Is there a way to define triggers so you can have a background worker query running and then you get asynchronous events somewhere else?
So I haven't used them recently. I think there is a way, definitely in Greenplum Database, there is a way of defining triggers. Yeah, maybe come talk to me afterwards and I can look it up. It's just not something I've used recently.